Let's get started. Wow, is it already the weekend? I see very few people here. That's good, you're the dedicated ones. Is this normal, by the way, in all classes? Usually Fridays are like this. I see a lot of nodding going on. I'm not used to this, so. I guess having the lectures online helps other people to skip class. That is clear. Well, then you'll have to ask questions that people won't hear I think there's still value in interaction in the classroom, but I cannot point my finger to it exactly. But there's some value. There's some different energy, I think, in the classroom versus outside the classroom when you're sitting there and listening to the YouTube or whatever video that you listen to. Okay, we're going to talk about GPUs. We're continuing this, and hopefully we're going to end this today. But this is actually, we've covered a lot of different processing paradigms, if you haven't realized. And these are all very interesting and very useful. And this is your reading. I warned you about it. And I may cover some other processing paradigms that we're not going to cover in this lecture. Actually, if we get to it, we'll talk about systolic arrays at the end. One of the things systolic arrays do is minimize memory bandwidth. And all of these paradigms that we've discussed so far are very processor-centric, right? We always bring the data into the processor. I may talk briefly about, in my inaugural lecture, whether we should be doing that going forward. Maybe we should be moving instructions to the data, instructions to memory rather than memory to instructions, right? Especially since things are very expensive today to move in terms of data. Why not put some processing unit inside the memory itself, and without moving the data, you do the processing. So I think there's a lot of future in that direction, which really doesn't exist in any of these paradigms that you've covered over here. These all assume that you have the data in memory, you have some instructions here, you move the data to the instructions. But if moving the data to the instructions is extremely expensive, is that a good idea to do? Anyway, we're not going to cover that in the lecture, but in this course, but you can attend this one to see a glimpse of it and what kind of benefits you might get from that. But let's go to SIMD processing. My hope is that we will be able to cover this also today, but let's see. I won't go into a lot of detail, in especially decoupled access execute. So we stopped at this slide, so hopefully you know what SIMD instructions are. Hopefully you know what a vectorizable loop is. What is a vectorizable loop? Anybody who's brave and not sleeping? Or vectorizable code? Yes? Exactly, yeah. A loop where iterations are independent of each other. There is no loop. There's also a loop carried dependence. There's no loop carried dependencies, basically. And that's vectorizable. This is an example of that. There is no loop carried dependence here. And if we look at it, the iterations look like this. I'm going to ignore the branch over here. And this is a way of vectorizing it. Basically, you take these two iterations and you put them side by side. And you take more than two iterations in this case. It could be your vector length. You put them side by side, and for each instruction that is the same, you generate a SIMD instruction or vector instruction. So you have a vector load, vector add, vector store. That's how you vectorize the code. So if you have a good programmer, clearly the programmer can understand the iterations are independent and do this in their head. If you have a good compiler, the compiler could do it also, right? The compiler can say, oh, this iteration is independent of this iteration, and I can prove that all iterations are independent, and they're all doing the same thing. So I'm going to put them together and pack them into SIMD instructions, vector instructions. So basically, vectorization is a compile time reordering of operation sequencing. Basically, you can think of this as you're sequencing through this operation sequentially. Instead, the compiler figures out that this loop is vectorizable, so it basically reorders the sequencing such that iterations are happening in parallel, And each instruction in the iteration is a vector instruction now. Now you're basically, the vector instruction spans the iterations. So of course, to be able to do that, the compiler needs to make sure that these iterations are independent of each other. In this case, yeah, it may be easy. Although it may not be easy also, because C may be overlapping with A, right? So the compiler needs to make sure that these arrays do not overlap with each other, right? Such that they don't, a previous iteration does not override a later iteration, right? This is called loop dependence analysis. And if the compiler doesn't know the addresses, remember, the addresses may be generated dynamically during runtime. And if the compiler cannot figure out the addresses at compile time, it will not be able to vectorize this code. But as a programmer, you may have that information. You may say, oh, I'm never going to have an overlap between these arrays, even though you may dynamically generate, because you may understand some semantic information from your program. You can easily say, oh, there's never going to be an overlap. The compiler cannot prove it, so it cannot vectorize, but as a programmer, you may be able to vectorize it much better. So there are levels of knowledge that happens at the transformation hierarchy, right? You're the programmer at a higher level, and you have a lot more semantic information. Of course, if you're the programmer and you miscalculate and you're wrong, then you get a wrong program. And that's one of the problems with parallel machines. When you try to vectorize your code, you may get wrong program because you may think that these arrays will not overlap with each other. Right? So even this simple piece of program is not easy for the compiler, and it may not be easy for the programmer also to vectorize. Okay. So this is the summary of vector processing. We're going to move to GPUs. I mean, there's a lot to be said in this, and as you will see that also, there are other ways of executing this program, and we will see this in a little bit. But this is actually essentially the beginning of a parallel computer architecture course. How do you actually design parallel machines? How do you program them? And how do you make sure they work efficiently? And how do you make sure they work correctly? Right? And whose burden is that correctness, right? Because there are problems you can encounter at any place. If you think sequential programming is hard, parallel programming is much harder. Okay, so basically, this is a summary. Vector or SIMD machines are good at exploiting regular data-level parallelism, as we've seen, and hopefully it's clear from this picture. Basically, you perform the same operation on many data elements. This improves performance, this simplifies the design, and this improves energy efficiency also, because you fetch much fewer instructions. It's always the case that performance improvement that you get from any machine, any parallel machine, is limited by the vectorizability of code. So if you have no loops that are vectorizable, too bad. If 90% of your program is vectorizable, what's the maximum speed up you can get? Yes? 10 times, exactly. If 90% is vectorizable, assume that you have an infinite number of processing engines, infinite number of lanes in your SIMD machine, or infinite number of functional units. You can get rid of that 90% and you're left with the 10%. 100% divided by 10% is 10x. So you get 10x speed up in that case. So 10x is not that high, right, with infinite number of processing elements. So you really want your program to be very vectorizable in the end. So if only 50% of your program is vectorizable, whatever you do, you can get only 2x speed up. So you really want to increase the vectorizability of your code. If it's 99% vectorizable, you get 100x, which is still not that high compared to infinity. Okay, so this is Amdahl's law. You know this, basically. Which means that scalar operations limit vector machine performance. And this is true for any parallel machine. If you have a multiprocessor, the non-vectorizable, non-parallelizable part of your code limits your performance. Which means that as a parallel machine designer, you have to be smart. And Cray, when they designed Cray 1, where it's smart, they didn't say we're going to design the fastest parallel machine, but it was actually the fastest scalar machine of its time also. Remember the heterogeneous picture where they had the vector units and the scalar unit? They said we're limited by this Amdahl's law, so we're going to design the fastest scalar machine such that when we're executing through the sequential part of the program that we cannot vectorize, we're going to go really fast and minimize the impact of that scalar part. Does that make sense? So this is when people think about Cray, they think about it's the fastest parallel machine, but this is one of the main reasons, actually. They really optimize that scalar part. In fact, Amdahl's law, when it was written in 1960s, 1965, 67 to be precise, Amdahl, he did the analysis of the vectorizability of the programs at the time, like data-intensive programs at that time. This is 50 years ago, of course, very different programs. And he found that a lot of the programs are vectorizable by about 60% or so. So his paper was actually relatively pessimistic. He said that you need to actually invest into sequential execution to be able to make a parallel machine work, because only 60% of the programs, 60% of the program is parallelizable. So if you read Amdahl's paper, which I should have referenced here, but maybe we'll put it up online afterwards, you will get that. So never forget this. Whenever you design a machine, the part that you're not able to parallelize will come and bite you in the end. Okay, so SIMD has been very, very successful. Many existing ISAs actually include vector-like SIMD operations. And I'm going to show you examples of this. And you may have heard of some of these acronyms. ARM has, I don't know, maybe they have a new one right now. But Intel has AVX right now. They used to have MMX, which I will talk about. So what are these SIMD operations? These are actually a pretty limited form of SIMD. Remember this, we've already talked about the SIMD. These are extension instructions, basically. A single instruction acts on multiple pieces of data at once. And the reason they were introduced, as I will show you in the next slide, is because of graphics. And basically, instead of interpreting a data element as a 32-bit word, this should be 0 through 31, by the way, but that's okay. You interpret it as 4 8-bit bytes, right? And then you basically add those 8-bit bytes, yes?
What's the difference practically between an extension instruction and a regular?
Oh, basically it's a regular instruction, but it was added to the ISA later on. You always keep extending the ISA because you find out that, oh, you need this instruction to go faster. So x86 ISA, for example, has been present for a long time, but they introduced in 1996 actually, these MMX extensions. It's still a real instruction, but they're extending the ISA, basically.
CPU doesn't make any difference.
So that's a good question. I mean, for any instruction, the CPU can do something special, right? So initially, they were executed in a separate part of the functional unit. Actually, the floating point extension, for example, when x86 introduced it, there was a floating point coprocessor. So it was really executed on a separate coprocessor, if you will. Later, it got integrated into the pipeline. So I say extension here because it was extended, but I mean, you can always move existing instructions out of the processor also. But that's a very good catch. That's a good question. Okay, basically, instead of interpreting a value as 32-bit value and doing a scalar operation on two 32-bit values, we interpret a 32-bit value as 4 8-bit bytes and then do 4 adds, 4 byte adds, basically. And that's the specification of the instruction. And this is a packed add. It's called a packed add. You pack 4 adds where each add is 8 bits wide. Basically, that's a SIMD operation. Very limited SIMD, right? But it is SIMD. So let's take a look at Pentium's MMX operations. The idea is very similar. One instruction operates on multiple data elements simultaneously. It's very similar to array processing, actually. If you want to be a purist, this is really array processing, right? You have multiple data, and you're operating on them at the same cycle, at the same time. And again, this is designed with multimedia operations in mind, and we will see an example of it. So this is exactly the same previous picture with the numbers a little bit corrected over here. So what's the difference? There is no vector length register, because your vector length is really specified by the instruction opcode. So opcode determines the data type. Basically, an opcode can say, I'm going to interpret the 64-bit value as 8-bit bytes, and do 8, adds, multiplies, whatever the opcode is. Or I'm going to interpret this as 4 16-bit words, and do 4 16-bit adds. Or I'm going to interpret this as 2 32-bit double words and do 2 double word adds, or I'm going to interpret as a single scalar 64-bit quad word in Intel's terms and do that. And all of these are distinguished based on the opcode instruction that you have. Yes?
So if you have a 64-bit adder, for example, can you just turn off the carry?
Exactly, yeah. Basically, if you go back here, you need to enable this to make it work. You can eliminate the carries and do it that way. So you'll need to modify your adder to make it work, of course, and that's exactly what they did. This is the minimal thing that they can do to enable these operations without modifying the pipeline that much. Okay, basically you change your ALU control. Okay, and this is a beautiful paper. If you're interested in reading about this, this paper is actually one of the very clear industry papers that introduces this, multimedia extensions. And they introduced it because they figured out that there's a lot of this kind of operations, for example, on pixels, in graphics, multimedia processing, and Intel processors were not good at handling these operations because these were not 64-bit, not wide operations. These were usually 8-bit or 16-bit operations. And they wanted to do more operations per cycle. And that's exactly why it's introduced. So let's see an example. This is a simple example, which may look complicated. This is directly from the paper, and my copy was not that great. Maybe you'll have a better copy. But basically, the idea over here is an image operation. You have this picture of a lady, and you want to substitute the background, which happens to be blue, but you cannot see the blue over here. And lady is hopefully not wearing blue, and not have blue eyes, I assume. Basically, we want to substitute the background with this picture of the background image, which happens to be, I don't know, some tree, I guess. This is called chroma keying, basically, image overlay using a background color. So what you do over here, let's assume that the images are equal size. What you do over here is we would like to basically get a bit mask of only the blue parts or the non-blue parts. Of the image. So we operate 1, 2, 3, 4, 5, 6, 7, 8 pixels at a time. You load 8 pixels at a time into these multimedia registers, that they call them multimedia registers. And let's start with these 8 pixels over here. Basically, you compare those 8 pixels to this blue vector. So this is the encoding of the blue in terms of the pixel. And you check whether the 8 pixels that you've loaded from this image is equal to blue or not. Basically, that's a packed compare equal byte. That's what this stands for. You have each byte compared to, I don't know why it's a byte, but anyway, you can read the paper. But I'm going to assume it's a byte. Basically, it turns out that these 8 pixels that you have, this is not blue, this is not blue, this is blue, this is blue, this is not blue, this is not blue, this is blue, this is blue. And this pack comparison compares whether each pixel is blue or not. Basically, there's a value for blue. If it matches, you get all Fs, all ones. If it doesn't match, you get all zeros. So in this case, you can figure out which ones match and which ones don't match. So these pixels over here match, apparently, and these pixels over here don't match. So this must be somewhere from that part of the image. Make sense? Basically, you figured out which parts of the image are blue or not. You do it for the entire image, but this is one instruction. So you need to have a loop to loop through the entire image. And what you do after that is, if you want to do the overlay for the pixels that are blue, you want to replace them with the pixels that are corresponding in this image. For the pixels that are not blue, you want to replace them with the pixels that are corresponding in this image. That way, hopefully, you will get this image. Okay? And that's what this does, basically. This does a packed AND of this bit mask that we've computed based on which pixels are blue. And it replaces the blue elements with the data that comes from this blossom image. Okay, that was the word I was looking for. So the blue elements here get replaced with the blossom image. As you can see, we're ANDing here. And this is an AND NOT, or NAND, basically. We replace the 0 ones with the pixels that come from the lady's image. And then you do a packed OR on these results, such that you can combine the two images. And packed OR simply, these are 0 over here, we didn't modify, but we get the values from the lady's image. And here, the non-zero values come from the blossom image that we're overlaying into. And they would hopefully be 0 in the lady's image, or after this operation. And you basically merge them using a packed OR. Make sense? So it's pretty simple, actually. You just, and then you can encode this with all of these instructions. So you need to move. You need to move the data from memory into the MMX registers, and then do a pack compare equal byte, and then packed and not, and then packed OR, and then you're done. And then you do a loop across the entire image, all of the pixels on both images. Okay, so hopefully this shows you an example of where these SIMD operations, even in a very limited form, could be useful in image processing. And in image processing, you have millions of pixels, especially if you're doing high-resolution images, high-resolution videos. That's a lot of pixels. So even doing this on 8 operations is good, because it improves your instructions per cycle by 8, if you will, instead of doing it 1 by 1. But you could easily do it for 1 million pixels at a time, right? And that's where GPUs come in, basically. GPUs were initially developed to do the processing of things like this, images, videos, graphics in general. I'm going to give you a view of them in the more general purpose perspective. We're not going to touch the graphics parts a lot, because if you want to go into graphics, that's a course by itself, really. Both graphics hardware as well as the software. So GPUs, by the way, any questions on that image before? I recommend that you read that paper, actually. Maybe I should assign that as a reading rather than the other GPU paper. Maybe we'll have 2 readings, since these readings are really not covered in any textbook, but the field has moved a lot. If you don't know GPUs today, you're at a disadvantage very quickly. That's why it's not covered in the previous textbooks, right? Textbooks always follow what happens in real life. Okay, no questions, so we'll go to GPUs. So GPUs, basically you really, oh yeah, there's a question in the back. Yes, thanks.
Is there a difference between a packed and a regular and?
Is there a difference? Well, I think that's a good question, basically. What you're saying is, why didn't we use a regular AND over here, right? I think the reason is regular AND, I don't believe is specified to operate on these MMX registers. It's really, but I agree with you. This could have been an and they could have given an MMX argument. They didn't do that for some reason, because they specified. I think the reason was, which I agree with, they were principled. Anything that operates on MMX registers are going to be called packed, even if it's doing the entire AND. That's a very good catch. Send me an email after class. Or not right now. Okay. Okay. So GPUs are SIMD engines underneath. You've actually seen all of the principles, except for the integration of the principles. The instruction pipeline operates like a SIMD pipeline, like an array processor. However, you have not seen something, which is the programming. The programming is done using threads, not SIMD instructions. That's why GPUs have taken off a lot, whereas vector processors have been very specialized to high-performance computing. So to understand this, we should go back to our parallelizable or vectorizable code example. By the way, if I say vectorizable, it's the same thing as parallelizable. People use these interchangeably. But first, we need to distinguish between 2 things. One is the programming model, which is a software, and the other is the execution model in hardware. And we've seen the distinction a little bit earlier, but let me clarify that a little bit. So the programming model refers to how the programmer expresses the code or views the machine, right? And we've seen sequential, von Neumann model. We've seen the SIMD model, data parallel. We've seen the data flow model. If the programmer is expressing things as those data flow graphs, that's their programming model. We haven't seen as much the multi-threaded model, but we've talked about it, right? You basically have different threads having different program counters and executing separate pieces of code. And I'll introduce the term SPMD in a little bit. Execution model, on the other hand, refers to how the hardware actually takes that code and executes it underneath. And these don't need to be the same. For example, we've seen out-of-order execution, which took sequential piece of code and executed in out of order, right? Vector processors, array processors, data flow, multiprocessors. We've seen multi-threaded processors, fine-grained multi-threading, right? You have multiple threads, multiple program counters, multiple register files, and you do multi-threading in hardware. And these two things could be very different. Execution model can be very different from the programming model. And this is one example that we've seen very well. A GPU, it turns out, is an SPMD model, very close to multi-threaded. It's really a multi-threaded model implemented by a SIMD processor underneath. And we'll see what those things are. Basically, you have multiple threads, but a GPU dynamically combines them into vector-like instructions. So let's look at these different, example a little bit. This is the example that we had, scalar sequential code. We're going to look at how to do it sequentially, which is not so interesting, how to do it data parallel, and how to do it in a multi-threaded fashion, which will be the newer part. So this is the sequential code, and it looks like this, basically. You need a branch, of course, but I'm going to ignore that for now. This can be executed on a pipeline processor. You've seen out-of-order execution processor. That's also you've seen. Basically, independent instructions are executed when ready. If you have an out-of-order processor, basically different iterations can be in the pipeline at the same time, right? This load may take a long time. And this add and store may depend on it, so they'll need to wait in the reservation stations. But these instructions can execute, right, in an out-of-order processor, because this is from a different iteration. They're independent. And they can execute in parallel. And basically, how good an out-of-order processor will be on this code is dependent on how long your latencies are. Because if your latencies are only 1, out-of-order processor doesn't buy you much performance, actually any performance in this code. And second, how far ahead the out-of-order processor can look, how big its reservation stations, how big its instruction window is. So if this load takes 500 cycles, the out-of-order processor can look ahead 500 instructions. Basically, it can cover 500 divided by 4 iterations, right? Ignoring the branch again. And it can find the instructions from that later iteration at the very bottom and then execute them in parallel with the load that's still waiting waiting its data. So that's the beauty of out-of-order execution. You can look ahead in the sequential code and execute. In other words, basically, if you think about this a little bit, the loop is dynamically unrolled by the hardware. How many of you know about loop unrolling? Okay, some of you. I don't think you should have seen it in any class. Basically, loop unrolling is a compiler optimization where the compiler takes the iterations and combines them. It takes multiple iterations and combines them into a single large iteration to eliminate the branch. So if you know that this loop is going to iterate 1,000,000 times, to get rid of the branch, you unroll it and put together, I don't know, maybe 500 iterations together. That way you reduce the branches in the code. You have one branch every 500 iterations instead of one branch every iteration. Right? An out-of-order processor does something very similar, basically. It looks ahead and it basically sees many iterations inside the machine and finds independent instructions. So a superscalar processor can take this and can fetch and execute multiple instructions per cycle, right? So if you have out-of-order superscalar, now you can do more, right? A superscalar processor basically doesn't need long latencies. It can execute multiple instructions per cycle. As a result, it can improve performance. But basically, we've seen that this code can be executed in a superscalar manner by fetching and executing multiple instructions per cycle also. And VLIW, we've also seen the compiler can somehow pack these instructions, independent instructions, together and execute them in a VLIW manner. So, for example, a smart compiler can pack these loads from independent iterations together into a VLIW instruction, right? So you have, if your width is 8 wide, you can have an 8 wide load. But you have 8 loads in the VLIW instruction. That's the difference from SIMD, right? Instead of having a single load that says you do it 8 times on 8 different data elements, you can pack these 8 different loads from 8 iterations into a single VLIW instruction, except your instruction would be really long, really large. But you can also pack other things together. The VLIW compiler can say, oh, I want to pack this add and, well, I cannot do the add and store. I want to pack this add over here with the load over here. There's no reason you cannot do that because they're independent of each other. Okay. So basically, we saw a lot of techniques to improve the sequential execution model. The programming model is sequential, but if you look at this, the execution model is very different. Okay. So let's look at the data parallel programming model. Data parallel programming model, somebody needs to take the scalar code and realize each iteration is independent and reorder the operations such that it looks like this. Basically, the programmer or compiler generates a SIMD instruction to execute the same instruction from all iterations across different data. This should really be called operation in this case, because it used to be instructions in the scalar model, but we're going to take these operations that are doing exactly the same thing, pack them into a single SIMD instruction. And that's what we did earlier. So this is called a vector instruction, basically. And vectorized code looks like this. You have a vector load. You're loading from a base address array into V1. You're loading B into V2. You're doing a vector add. And you're doing a vector store. So that's beautiful. And this is the programming model. Basically, your program looks like this. And think about the execution model. Like, what does the hardware do? This is really best executed by a SIMD processor, a vector or an array processor. If you take this beautiful piece of code and execute it on a pipelined in-order processor, you're really doing no justice to someone who's done a lot of work to optimize a program, right? You could, right? There's no reason why you cannot take this code and translate it into an in-order pipelined, or even not pipelined, processor, right? Remember, you can always take the code and turn it into a single scalar instruction at a time and execute it. Not to have multiple functional units. That's the beauty of architecture. You have this code, software at the top, you have this hardware, and you can do anything in between to make the hardware really simple, or to make the software really simple, by doing translation, right? But somebody went through a lot of pains to execute this code. Why would you actually reduce it to execute on a really simple in-order processor? That makes no sense. So this is really best executed by a SIMD processor. Okay, so let's look at the third programming model. This is multi-threaded. Basically, I've already given you the idea. You need to, again, realize each iteration is independent over here, and you turn the iterations into different threads. So the programmer or compiler generates a thread to execute each iteration, and each thread does the same thing, but on different data, in this case. So I'm going to assume that programmer takes only one iteration and makes it a thread. Now you can say that, oh, that's too short. Why don't we pack together 10 iterations? And then that's a thread. That's true, and that's also done, but I'm not going to simplify the explanation, I'm going to assume one iteration is a thread for the rest of this talk. So this can be executed on a MIMD machine. MIMD, remember, multiple instruction, multiple data. Basically, multiple threads. This could be executed on one processor. This could be executed on another processor, on another processor, another processor. Now you parallelize your code on a multi-processor, which we have not talked about as much, but the concept is very simple. You have multiple processors. Or, well, what is a MIMD machine? It could also be executed on the fine-grained multi-threaded machine that we've discussed, right? These are all independent of each other. So you have multiple threads in the fine-grained multi-threading. Remember, multiple program counters, multiple register files in a pipeline machine. Every cycle you fetch from a different thread until you finish all the threads. That's also a MIMD machine. So you actually have seen MIMD machines. Fine-grained multi-thread machine is really a multiple instruction, multiple data machine because it executes multiple instruction streams. So a thread is also called an instruction stream, if you will. Okay, so this programming model actually has a particular name. Multi-thread is very general. In this case, the realization is that each thread is doing exactly the same thing. It's exactly the same code, right? There's no difference between threads. They're executing exactly the same code. So this particular model is called single program, multiple data. Basically, if you look at each thread, it's really the same program, but you're really operating on different data elements with that program. This is operating on the data elements that belong to the first iteration. This is operating on data elements that belong to the second iteration, zeroth elements, first elements, second elements, third elements, ... So that's what the single program multiple data. Sometimes you may see single procedure multiple data also over here. You can call it single thread multiple data also. So this the realization is that, the GPU realization is that this can be executed on a SIMD machine, basically. You can take this single program, multiple data, multi-threaded program, and design a much more efficient machine than a multiprocessor. A multiprocessor replicates many processors, so it's not very efficient. But GPU says, oh, my hardware is going to be very SIMD-like, single instruction, multiple data-like, so I'm going to take this programming model and execute it on a much more efficient machine. That's why GPUs are, if your code looks like this, you'd better execute on a GPU and not a multiprocessor, because you'll waste a lot of efficiency on a multiprocessor. Whereas in a GPU, it's going to combine those things into vector instructions. So basically GPUs, they're SIMD machines, but they're also called SIMT machines. I'll have to give you the terminology because you may see this later on. It's also called single instruction multiple thread. Basically, you have multiple threads, but you combine the same instruction from those threads into a single instruction and execute it on parallel functional units that do exactly that instruction. So we'll see that. So basically, a GPU is a SIMD machine, except it's not programmed using SIMD instructions, as I've just said. It's programmed using threads with that SPMD programming model. Each thread executes the same code, but operates on a different piece of data. And each thread has its own context. This is obvious. It can be treated, restarted, executed independently. It has a different program counter. It has a different context, basically, different registers. But we will see why this is useful. This is useful, actually, because you can move the threads to different places, right? You can decide, oh, I know that iteration 1 through, I don't know, let's say 16. Let's say you have 16 parallel function units. I know I have 16 parallel function units. One way I can do execution is I'm going to combine 16 iterations, consecutive iterations together and execute them together. But you can really pick any thread from any iteration and put them together, because they're all independent. Okay, this will be clear soon. So let me define you more terminology. Basically, a set of threads executing the same instruction is dynamically grouped into a warp or wavefront. Warp is the NVIDIA terminology. Wavefront is the AMD terminology by the hardware. And we'll see an example of this. A warp basically is a SIMD operation formed by hardware. I'll give you, actually, go back here. So this is your multi-thread model. You have these loads that are exactly the same thing, right? It's the same load operating on different data elements. So we're going to combine these into a warp, let's say 16 of them, or 32 of them. And we're going to treat them as a single entity. Except each operation will operate on a different data element, but it will look like a SIMD instruction, SIMD operation. Okay. So warp, remember, it's a set of threads that execute the same instruction. They're all at the same program counter over here. Okay, we already talked about this. So let's look at how a warp is formed by the GPU. Basically, a GPU takes these warps. This is an example of a warp. You have warp 0 at program counter X. That means you have multiple iterations, multiple threads inside that warp, and each of them are doing the same load, but on different data elements. Makes sense, hopefully. So this is warp 0. So when you can fetch this, you can fetch from this load, which means that you'll be fetching multiple loads. And then the next instruction you fetch from this warp will be the instruction that's at PC X plus 1. And then when it's done, you fetch from the next instruction. And then when it's done, you fetch from the next instruction. Make sense? Basically, it's like SIMD instructions, but there is no vector code over here. You still program with loads, adds, and stores, except you indicate that they're warps, and you keep fetching from these warps. So let's look at it in more detail. Any questions so far? This is hopefully clear, right? Yes?
Why is it useful? It seems to me that it's not much more difficult to just program it as a SIMD
machine.
Than doing threads.
Okay, that's a very good question. Well, let's defer the answer in a little bit, because threads are easier to deal with from the programmer's side, and SIMD is not very flexible. That's one of the main reasons. But we'll get to it toward the end. Let's understand the model first. Basically, in SIMD, a single sequential instruction stream, you have a single sequential instruction stream of SIMD instructions, right? It's sequential. So you will see that, actually. Maybe we'll start that. Each instruction specifies multiple data inputs. So you have vector load, vector add, and vector store. And you need a vector length. Basically, we're going to eliminate that vector length over here. If you think about SIMD, it's data parallel, but it's instruction sequential, right? There's no concept of threads in there. So you're limited by sequential execution in the end. We've eliminated that sequential execution. That's one of the answers to your question. There are multiple answers. And the second is programmer now needs to deal with this vector length. GPUs can make it a little bit more flexible. So SIMT, on the other hand, multiple instruction streams, single instruction, multiple thread. You have multiple instruction streams of scalar instructions. First of all, you don't need to think about vectors. You can think scalarly. But you will need to think about arrays still. But threads are grouped dynamically into warps. So what you have is really scalar instructions, nothing different from your existing single instruction, single data programming model, but you specify a number of threads that you operate on. And depending on how the GPUs actually expose this to the programmer, you may need to specify the warps also, but let's not get into that. I think there are some inefficiencies in existing systems for that. Does that make sense? So I think, let me answer part of your question to begin with. This is inherently a little bit more sequential, whereas here you have many, many threads, so you have more flexibility. And the second is, this is a bit easier to program because it's not different from writing a single sequential program, right? You don't need to think about vectors and vector length. And vector length actually causes some other issues in the machine. If you need to change the vector length, you'll need to stall the pipeline, if you remember that we've discussed before. Yes?
But it does add overhead, right? The hardware needs to match the threads to
Yeah.
the cores or something.
So if the programmer specifies that, it doesn't add that much overhead. Right. But if you want to do fancy things, yeah, you need more overhead, yes. Okay, so there are two advantages. Basically, you can treat each thread separately, aside from what we've discussed. You can execute each thread independently on any type of scalar pipeline. So this leads to MIMD processing. And we'll see examples of this. And you can group threads into warps flexibly. Basically, you can group threads that are supposed to truly execute the same instruction underneath in hardware. This is a bit harder to grasp. We will see this a little bit more. But let's take a look at this one first. Yes?
What exactly is the difference again between a SIMD instruction and a scalar instruction?
A SIMD instruction, basically, it's inherently a vector instruction. You have a length. You basically do a vector load. You operate on vector length number of elements. A scalar instruction is just one element, one pair of elements. Make sense? So, for example, let's go back to here. Okay. So you do a load, you load one piece of element, one element. Whereas here, you do a vector load, you load vector length elements. Okay. So let's look at the multi-threading of warps. Basically, assume that we have a warp that consists of 32 threads, which means that you have 32 threads that are executing this program. And 32, a warp, if you remember, let's go back actually over here, it's a set of threads that execute the same instruction, right? They're at the same program counter. So we're going to synchronize them together. Basically, you have 32 threads, 32 instructions that are at the same load over here. Now, how do if you have 32,000 iterations over here and a warp, so warp is really a hardware construct in the GPU. A GPU says, I can execute these 32 threads at the same time at the same program counter. But you may have many, many more iterations than 32, right? So if you have 32,000 iterations and you want to partition your program such that you execute one iteration per thread, you really have 1,000 warps in the end. And assume that those 1,000 warps can be in the machine at the same time. And these warps can be interleaved on the same pipeline. This is, remember, fine-grained multi-threading. Let's finish this because we want to get to a good point over here. But basically, you can interleave these warps on the same pipeline. You can do fine-grained multi-threading of warps. So let's take a look. Let's say this is your warp 0 at program counter X. You have 32 of these iterations bundled into it. and you fetch this one. In the next cycle, you fetch warp 1 at program counter X, the next iterations. In the next cycle, you can fetch warp 2. In the next cycle, we can fetch warp 3. In the next cycle, you can fetch warp 4, ... Right? Basically, you're multi-threading across this granularity of the warps. Now, you can also have warp 20 at PC X plus 2 executing somewhere in the machine also, right? And that's basically, you can calculate what iteration it's executing. It's really executing this iteration, 20, because we have 32 warps. You really have 641. This is the 641st iteration over here. Or maybe I started with iteration 1, so I ignored iteration 0, so that's fine. So this is correct. Basically, you can have many warps in the machine, and they can be interleaved together. A GPU interleaves them in a fine-grained manner. So let's look at this again. So you have these scalar threads. We've grouped them together such that they have a common PC. So this is a warp. And remember again, a set of threads that execute the same instruction is called a thread warp. It's SIMT. And again, SIMT is not a very common term. NVIDIA uses that, but some other companies may not use it. All threads run to the same code. And you have many of these thread warps inside the machine. So now this is looking like a multi-threaded machine, fine-grained multi-threaded machine, right? Except it's fine-grained multi-threading across the warps. So you may have lots of warps over here, and you push one into the pipeline every cycle. You fetch from this warp, and then the next warp, and then the next warp, and then the next warp. Now you may ask, what's a warp? Like, why is it called a warp? Basically, the threads that run lengthwise in a woven fabric, if you go to the dictionary definition of a warp. Somebody wanted to play with the word threads. Basically, you have multiple threads that are running lengthwise, and it's basically a woven fabric together that are put together. Okay, let me see. Actually, let's go a little bit more. Basically, it's called a shader core also. You don't need to know all of this terminology over here, but a GPU core is called a shader core because of graphics reasons. And it looks like this. Basically, you have program counter, mask. Remember the mask? That's we'll see that later on. This is basically a warp. And you have many warps. And every cycle, you send one of the warps to fetch from the iCache. And that warp gets decoded and executes on the scalar pipeline, but executes basically on different data elements. So we will see that this looks like vector lanes. And then once the warp is done, it goes back to this queue, such that it can get executed in the next instruction. You can now fetch the next instruction from that warp. In the meantime, once this warp is basically once this warp has moved to decode stage, you can fetch another warp. And then once this warp has moved to its pipeline, you can fetch another. The next warp you fetched moves to the decode, and you can fetch another warp. So basically, you're really multi-threading across the warps that you fetch, and each warp is really multiple threads grouped together into a single program counter. They're at the same program counter, but you operate on different pieces of data. So hopefully this is clear. Okay, so this is another view of it. It's a little bit more detailed, if you will. So why this is, you have these warps available for scheduling here, and this is the SIMD pipeline over here. But each lane is what we've seen earlier, basically. So why is it fine-grained multi-threading? Because you have one instruction per thread at the pipeline at a time. So there's no interlocking. That was the benefit of multi-threading. And you interleave this warp execution to hide latencies. So remember, a long time ago, I showed you the heterogeneous element processor. And it had these queues. There was a fetch queue. It had these threads waiting in the fetch queue. Now we have these threads, but again, threads are grouped into warps. And then if a thread gets a cache miss, for example, if it needs to wait for memory for 1,000 cycles, you take out that warp, move it into this waiting queue, and it sits in this waiting queue for a while until it gets its data, and it moves back into the pipeline after it's done, after it gets its data. So basically, we're treating things at the granularity of a warp, and we're scheduling things at the granularity of a warp also. You're fetching at the granularity of a warp, and you're waiting at the granularity of a warp. And this is nice because these threads are taken out of the pipeline, they're waiting over here. Hopefully there are many, many other warps that are coming into the pipeline that can hide the latency. Right? and you see the register file over here. This enables long latency tolerance because, again, in graphics, you have millions of pixels, right? Remember, if we're doing the same code that we've seen in MMX, you have this, it was, I think, 7 instruction length code. Each thread does 7 instructions, but you have millions of pixels. If you assume that a warp is 32 threads, you divide a picture that has millions of pixels into warps of 32. So you have 1,000,000 divided by 32 warps. So your latency tolerance is really huge. Even if one warp waits for 1,000 cycles, you have thousands of other warps that are coming into the machine. Right? Okay, let me finish this also, I guess. So recall this slide. Basically, if you have a 32-thread warp executing an add, inside the machine, you could actually do something like this, right? You could actually have a vector machine that looks like this. But you could also do this. You can have 4 functional units and executes 4 of the threads of a warp at the same time. So remember, if you have a 32-thread warp, you have 32 threads, 32 data elements. You can do each of them every cycle. This is the first element, first thread, second thread, third thread, fourth thread, fifth thread, ... This is like a vector processor underneath. Or you could do much more like a GPU. You could do 4 of the threads of a warp at a given time, and then the next 4, and then the next 4, and the next 4, and the next 4. And these execute on lanes that look like this. So we've seen exactly the same thing before, except instead of having a vector registers, we have registers for different thread IDs. So we have partitioned our register file. This lane over here has registers for threads 0, 4, 8, ... This lane over here has registers for threads 1, 5, 9, ... It's beautiful, right? Okay, I'll finish with this slide, I think. And then we can take a long break and then we can come back. Basically, again, let's take a look at this example. You've seen this before. We can overlap execution of multiple instructions. An example machine that has 32 threads per warp and 8 lanes. Which means that every cycle, we issue 8 threads from a warp. We can complete 24 operations per cycle while issuing 1 warp per cycle. So basically, this is the first warp, warp 0. It's executing this load unit. So you basically send it in the first cycle, 8 of these threads. In the next cycle, the next 8 threads. In the next cycle, the next 8 threads, ... So you have 8 lanes in your machine. In the next cycle, you fetch from a different warp, because we're doing fine-grained multi-threading. And in the next 4 cycles, we're going to send the threads, the 32 threads from this warp. In the next cycle, you fetch from a different warp. In the next cycle, you fetch from a different warp, different warp, different warp. So if you overlay this picture with the SIMD machine, you'll get exactly the same thing, right? Except these are called warps over here now instead of vector load, vector multiply, vector add. Okay. Let's stop here. Let's take a 15-minute break and come back at 14:23. There you are. All right, it's already 23, so let's get started. So I want to go over this picture one more time because I kind of rushed it a little bit. Even though you've seen this picture before, it's a little bit different here. Basically, this picture builds upon this picture over here. So here we have a warp that has 32 threads. You're basically executing the same instruction across 32 threads or 32 pieces of data elements. They're doing 32 different iterations, right? Now, if you have only one functional unit that looks like this, you execute them in 32 cycles, right? That's this example. If you have 4 functional units, you execute 4 of the threads in a warp in one cycle, and then the next 4, and then the next 4, and then the next 4, and then the next 4. Now your performance has increased. You can finish this entire warp in 8 cycles because you have 32 threads per warp, and you're doing 4 threads per cycle. Threads equals iterations in this case, right? And this picture is exactly the same as what you've seen in the SIMD instruction earlier. This is a vector add, right? So if you had 32 functional units, then you would execute all 32 iterations or 32 threads in one cycle, right? So the reason you have, basically somebody needs to determine how many functional units you have, and that's the hardware. And you may specify some number of threads per warp, and in that case, that gets executed in different number of cycles depending on the hardware you execute on. So if one GPU, for example, may have, hopefully not one, but 4 functional units per lane, or 4 functional units or 4 lanes. In that case, in that GPU, a 32-thread warp will take 8 cycles to execute. Another GPU may have 32 lanes or 32 functional units. In that case, that same warp would take only 1 cycle to execute, right? Okay? And this is the lane as we've seen before. So to best understand this, you should really overlay this with the SIMD lecture that we had. So here we're assuming we have 32 threads per warp, but 8 lanes, which means that we can start 1 warp per cycle, but that warp is going to finish in 4 cycles in the load unit, right? Basically, for example, at time t0 over here, we'll start warp 0. This is 1 cycle over here. In the first cycle, you'll finish 8 of the threads. In the next cycle, you'll finish this next 8. In the next cycle, you'll finish that next 8. In the next cycle, you'll finish that next 8. Now, the warp is done with all 32 threads. Now what happens is you increment the program counter and you move to the next instruction in this warp. And remember the next instruction, you're doing a load, another load, and then add. What was it? It's an add, I think, and a store. Yes. That was our thread. Load, load, add, store. So this load, once this load is done, the next warp will go, the same warp will go to the next load. Once that load is done, the same warp will go to the next add. Once that add is done, the same warp will go to, I guess here we don't have a store unit, but to the store unit, right? Yes?
Maybe I missed it, but why do we put more than 8 threads per warp?
Yeah, so that's, we didn't go into the programming model as much, but somebody needs to specify the number of warps. And the question is, who does it? In current cases, it's really the programmer specifies it. But there is really no reason for the programmer to fully specify it. But why would it be higher? Because again, it's a contract between the software and the hardware. The software says, oh, I have 32 warps, but then the machine may have a small number or a big number. So it's usually good to have it a larger number such that the machine can have more flexibility in executing it with the number of functional units it has.
But if it was done, the warping was done by the
hardware, yes.
Hardware, I could just do 32 threads and it would split it over 4.
Exactly, yes. So there are other trade-offs, but let's not go into that. You're right, absolutely. If the warping is completely done by hardware, you can match the warp to the number of units you have. But there may be other reasons like control overheads. Let's not go into that because you may need to identify the warps in terms of, you may have state that's dependent on the number of warps you have. And that may be a limited state. And you may want to put many threads into that. So that's one reason, for example. And that's actually the reason why you have more threads, more warps, more threads per warp than lanes in a GPU. Okay, so basically, at the end of 4 cycles in the load unit, this warp finishes and it goes to the next instruction. So while this warp is executing in its first cycle in the load unit, now some other warp, completely independent, is being decoded over here and starts execution in the multiply unit in the next cycle, right? That's the pipeline machine, basically. It's completely independent because it's executing completely different 32 iterations over here. And then it takes also 4 units. Of course, you can extend this in terms of how long it really takes, how long the multiply unit takes. We're going to assume that multiply unit takes actually 1 cycle. You basically start 1 instruction per cycle, and at the end you get the result. So at the same time, this warp is executing its first 8 iterations, or 8 threads. This add is being decoded, and then next cycle, it basically gets dispatched into the add unit. So that's how you get to execution. And once this load unit becomes free, another warp that's executing a load instruction can get scheduled onto this, that's being decoded, can get dispatched into this load unit. So it's really pipelining and parallelism at the same time. Makes sense, hopefully. So if you remember this picture from the SIMD lecture, these were really called vector loads, right? And vector add, vector multiplies. Okay, so let's look at the memory access a little bit. Basically, this should be obvious by now, but basically, same instruction in different threads access different data elements. So how do they figure out which data elements they access? They basically use a thread ID to index memory and access different data elements. So in this case, we have 16 threads over here, and we have 16 data elements from one array, let's say. You can extend this to the other array that you're loading. If you have 4 threads per warp, we can have 4 warps over here. And warp 0 looks like this, basically. You have threads 0 through 3, and they need to access memory locations 0 through 3. So you index the array with the thread ID. Right? In this case, location happens to be 0. So basically, the memory address of a given warp is calculated as the base address of the array plus the thread ID. Because that's how you grouped the instructions into threads. Each thread operates on a single data element. Make sense? That's pretty simple. Now, I'm not going to go through this, but this is just to show you the example over here. So this is a CPU code. And this is kind of the GPU code. You can ignore the thread ID. There's a way of calculating the thread ID, depending on how you block your program and constitute the threads. But basically, your code looks very similar if you look at this, right? It's essentially CTID equals AATID plus BBTID. And this may not be the exact way the GPUs are programmed today, but this is a good simplified example in CUDA, some version of CUDA. Make sense? So basically, this is exactly like you would program if you would think, if you think. There's no vector instructions here. It's just a little bit more management added to your sequential code. And there are many threads over here. That's why you need to somehow figure out the thread ID over there. So this is another sample GPU program. Again, you don't need to know this, but this is a little bit less simplified. I'll just point out that you basically, this exactly is the same, right? But if you really want to learn it, you should take probably a different class or learn it on your own. Okay, so let's wrap a little bit. Basically, we're looking at warp-based SIMD versus traditional SIMD. So what are the differences? So traditional SIMD contains a single thread. And this was in answer to your question earlier. You have sequential instruction execution, and you have lockstep operations in a SIMD instruction. So if you have a vector load and you're loading from 64 elements, if they happen to be in different, if one of them happens to get a cache miss, one of them happens to take too long, that's too bad. You need to wait for all of them to finish until you move to the next vector instruction, right? So this is the lockstep part. This is similar to the VLIW, if you remember. In VLIW, you had multiple operations. If one of them took long, all of the operations needed to wait because the execution model is really sequential. And programming model in this case is SIMD. There is no extra thread. Software needs to know the vector length. In a sense, you're encoding the parallelism in the vector length, not in the threads. And ISA contains vector or SIMD instructions. So warp-based SIMD, or GPU SIMT model, consists of multiple scalar threads executing in a SIMD manner. Basically, the same instructions executed by all threads. Doesn't have to be lockstep. So you can actually merge these threads in different ways. For example, if a GPU recognizes that this thread is executing at the same program counter as this thread, maybe it can merge them. Right? Of course, this requires hardware complexity, but it's possible to do it. And each thread, because each thread can be treated individually, right? meaning that it can be placed in a different warp. So programming model is really not SIMD. And software doesn't need to know the vector length because there is no vector in the end. So this enables multi-threading, and this enables flexible dynamic grouping of threads. We've talked about multi-threading, and we're going to talk a little bit more about this dynamic grouping. But the ISA is scalar in the end. Each operation, each instruction operates on scalar values. And SIMD operations are formed dynamically. So as you've seen, essentially it's SPMD, single procedure, single program, multiple data programming model implemented on SIMD hardware. Okay. So let's look at SPMD a little bit more. This is, again, single procedure, program, multiple data. Just to make sure this is a programming model. It's not a computer organization, right? Each processing element executes the same procedure except on different data elements. That's each thread, maybe I should not call it a processing element over here, but each thread executes the same procedure. And procedures can synchronize at certain points in the program. Remember the barriers that we've discussed a long time ago? But you don't need to know exactly how to do this programming. Essentially, you have multiple instruction streams that execute the same program. Right? So just to make sure this is written over here, you have each program or procedure that works on different data, and you can execute a different control flow path. So you've seen the different data part really well, but they can also execute a different control flow path. So how do you support that? Let's see. And many scientific applications are programmed this way. You've seen array addition, for example, matrix multiplication. You can basically express it in this single program, multiple data programming model. And many scientific processors are actually running things on MIMD hardware. GPUs are essentially program things in a similar way, except they run on SIMD hardware, as we've seen. Okay, so let's look into this part. We've covered all of this over here, SIMD, SIMT. And we've seen that you can treat each thread separately. Let's look at grouping threads into warps flexibly. So this is actually some advanced things GPUs do, but hopefully you'll see some similarities. So let's say you have a thread that's supposed to execute this thing over here. And it can have a conditional control flow instruction, right? In this case, you see one control flow over here and a bunch of branches because things are and a loop branch over here. So just imagine these things as instructions over here. You have an instruction and then determine which instruction to go to next. Another instruction, determine which instruction to go to next, and then do some stuff. And then your control flow basically looks like this. So each thread has these instructions, and threads can execute different control flow paths. So for example, one thread can take this path depending on the data value, because it's operating on array element 0. Another thread can take this path, because this if condition may not be evaluating to be taken to C, it may be evaluating to be taken to D. Another thread may be executing this path, another thread may be executing this path. We don't know where they execute, of course, until we execute the threads. But assume that we've grouped these threads into a warp, because you have, let's say, 4 iterations grouped into a warp. These threads will start executing, and while they're executing, we'll figure out that the next program counter, well, even here, after we execute this instruction A over here in this warp, we will figure out that the next program counter of the first 3 threads, I think it's first 3, yeah. First 3 threads should be B, and the next 3 threads should be F. Now the beauty is gone, right? Because these threads start out at the same program counter, but 3 of them want to go here, and 1 of them wants to go here. So how do you do that execution now? They're clearly not operating in the same instruction anymore. Yes?
We put a no in between A and F and between F.
Exactly. So that's kind of what's done, except it's a hardware no-op, and you've seen this before. So let's take a look at this. Basically, this is called branch divergence. But I'll give you the solution. But no-op, when you said it's a software no-op, you cannot do software no-op because they all need to execute the instructions, right? So this is the problem with grouping threads, right? They all, as long as it's sequential, they go through the same program counter sequence. But once you have a control flow, you have this problem that the threads that are grouped together are diverging from each other. This is called branch divergence. And this is why GPUs are not very good at irregular code. This is called irregular code. It's not a single piece of code where every thread does exactly the same instruction and there's no control flow. You have some irregularity based on the data that you process. You need to take different paths. We'll handle this, but it will come at the cost of some performance. So branch divergence occurs when threads inside warps branch to different execution paths. So let's look at, let's say we have 1, 2, 3, 4, 8 threads over here. We execute that instruction. The next instruction is a branch. That's good. We have 8 threads. We execute the branch. We figure out some of the threads want to go to path A, some of the threads want to go to path B after executing this instruction. So what does a GPU do? A GPU basically creates 2 warps. The first warp does the threads that need to execute path A. The second warp does the threads, or executes the threads that need to execute path B. And when they come together, when the next instruction is the same, the GPU merges them back dynamically. Now, we're not going to go into the hardware of how to do this. There's complicated hardware in GPUs to make sure this works. But you've seen this idea before at the vector machine. What was it called? Yes. Exactly. It's vector masking, masked operations. So basically what the GPU does is after you finish this branch, GPU figures out a mask. It's called an active mask, actually. It says, oh, the next set of threads should execute path A, should have mask bits set. And those are threads 0, 2, 3, 7. Just based on the condition of the branch, where the threads need to go. And the threads that need to execute path B, the mask bits are for threads 1, 4, 5, 6. Right. So you basically set the mask bits such that even though you're executing, you're sending all of those to execute on this instruction, only some of those will take effect. And the ones that will take effect are determined by the condition of the branch. And we call this predication, right? Predicated execution. Basically, the GPU has a predicate inside. Except GPU does it underneath. The programmer doesn't need to deal with this at all, right? The programmer just writes in threads and hopes that the program gets executed correctly. GPU groups these threads together into a common program counter and makes sure what the programmer expects gets realized by doing this. So this is how a GPU does branching. If you look at the vector machine, as a programmer, we needed to do masking, right? I needed to, for example, over here, show you how you generate the mask and how you complement the mask and you execute the other path. That's what we did. We created a mask over here, and some of the vector add instructions, let's say over here, were masked, and then we complemented the mask, and some of the vector add instructions got masked over here, and then we set the mask all to 1 again. So the GPU is doing all of that in hardware without requiring the programmer to do that. Again, all the programmer does is this. Write this code, except in the code form, not in this box form. Okay, so it's beautiful, basically. Same as conditional, predicated, or masked execution. And some of you recall this. That's good. So now you realize if you look over here, what's happening is only 50% of your machine is utilized at that particular point. You're doing an add. You have 8 lanes, but you're using only 4 of your lanes. So your efficiency of your lanes is really only 50%. So what if only 1 thread went here? Your efficiency would be 1 out of 8. Now if your machine has 64 lanes, only 1 thread takes the branch, your efficiency is 1 out of 64. Now quickly your efficiency degrades. You have this hugely parallel machine, but you're underutilizing it. This is called SIMD utilization. What fraction of the execution unit is kept busy with a useful operation? So can we do better than this? So let me give you an example. So if you have many threads, you can actually find individual threads that are at the same program counter and group them together into a single warp dynamically when you need it, and then break the warp later on if needed again. So this reduces divergence, improves SIMD utilization, what I just discussed. SIMD utilization is a fraction of SIMD lanes executing a useful operation, executing an active thread. Yes?
The data it operates on can only be the one in the array, right? It can't do like... So everything has to be combinational circuits inside of the... inside of one thread, right? Else you couldn't dynamically warp them together with something else.
What do you mean everything has to be combinational? So you need to ensure that the thread can its data correctly, yes.
So it can't have any state apart from the state inside the array.
Exactly, yes. Exactly, yes. So basically, the state consists of the program counter, which is going to be awfully equal for these things that you're grouping, and the register file. Now, the register file is inside the machine, so that's okay. You just need to be able to access the register file correctly. So you need to be in the correct lane, basically.
Well, it meant inside of the core there's no state.
That's right, yes. Exactly. Okay, so let's take a look at an example of this. Basically, this is called dynamic warp merging or formation. You dynamically merge threads executing the same instruction and form new warps that are from warps that are already waiting. Remember, we have lots of warps in the machine. Some of them are at some PCs, some of them are at other PCs. Now, if you figure out that, oh, my new warp needs to be at this PC, but I have only 5 threads active out of 32, maybe you find some other warps that have 5 other threads active, and you merge them together. Now you combine them. Now you have a much better utilized machine. So enough threads branching to each path enables the creation of full new warps, basically. So let's look at an example. You have warp X, warp Y, and warp Z. We're going to combine these. So it happens that this warp X has these threads active. Active meaning they have mask bits set to 1 after a branch. And this warp has these other threads that are active. You can combine them to be a more full warp, assuming they're at the same program counter, of course. And that's how we combine them, right? Does that make sense? Now these warps, these threads will get their data correctly because this is executing in this lane, this is executing in this lane. And remember the lane structure that we had over here? We'll have to go really quickly back to this picture. Where is it? Okay, there you go. So you have registers for thread ID 0, 4, 8, and here, and 159 here, 2, 6, 10 over here, ... So you need to ensure that the lanes of the warps are preserved. The lane of the thread is preserved because it's going into that location, lane, where the registers are located. So basically, you can combine these warps. If you look over here, it's not as perfect, right? Here, what happens is you have these warps that are active, and you want to combine them with this other warp, these threads that are active, the blue ones. These orange ones are also masked. They have their mask bits set to 1, so they're active. Now, how do you combine these two? You can fill in the blanks over here, but you cannot fill in the parts that have blue because you already have a thread over there, right? So you've combined you added some more threads to this warp, but some remain over here. Make sense? Now the good thing is maybe there's some other warp that will fill in this part, so you'll get 100% utilization over here, and maybe you'll fill this in with some other ones. So hopefully you'll reduce the number of warps, amount of waste that you have in your execution units. Okay, which is this hope over here. So if you have another warp that looks like this, now what you can do is, you can do that, right? So you merge 3 warps into 2 warps over here, assuming they're at the same program counter, executing the same instruction. Sounds wonderful, right? It's like filling in the blanks, basically, so that you can maximize the utilization of your machine. It's amazing that existing GPUs do this. It's some hardware, but they do it. Okay, let's look at an example. This is I'll go through the same thing just to emphasize it. Basically, this is this warp going into the branch, and it takes path A. Now, it so happens that you have another warp over here going into path A also. You can merge these things together. That's exactly how this happens in the previous slide over here. Yeah. Okay, you can study this. And I'm not sure if I have time to go over all of this, but if you actually take these slides and animate it, you'll see a nice picture over here of this exact full code where things get merged. And I'll recommend that you do that on your own and see how things behave. By the way, these bits over here, you basically here what we have is you have warp X and warp Y. They all start at the same point. And this is the mask bits. At this point, all threads in the warp are executing the same instruction, executing that instruction. But warp X, only the first 3 threads are executing instruction at B, and the other one goes to F. And warp Y, only the last 2 threads are executing the instruction at B, and the other 2 go to F. So if you actually animate this, you will see that you can create many warps over here in this example, toy example. So for example, over here, you can merge this thread B with another one over here, but then this one gets underutilized. But now you can merge things in the C and you eliminate one cycle. So if you do all of this, you will see that you complete the program much faster. But I'll leave you to do this. This is just fun. The basic concept, you can group threads at the same program counter together. That's it. Right? That's the basic concept. The rest is basically how do you design the hardware to make it efficient, which we're not going into over here. It's a beautiful, a very powerful concept. So think about how to do this in a SIMD machine. Can you do it? No, right? Because in a SIMD machine, a vector load specifies those operations to be very tightly coupled. You cannot take out this operation from a SIMD instruction and move it to some other operation. Here, we don't have the SIMD, single instruction model. We have threads. A thread is decoupled from the other thread. You're just grouping them or ungrouping them dynamically. That's why this is much more powerful, in my opinion, than a traditional SIMD machine. Of course, it has its overheads. It's powerful in the sense that you can do these combinations so you can get higher performance potentially. With every idea, of course, there's a downside, so you can guess what's the efficiency of the SIMD machine. SIMD machine doesn't need to deal with the threads, right? So there's no overhead of this thread management in a SIMD machine. You have a single thread. So there are always downsides and upsides of an idea. Okay, so I think I've given you this, but I'll leave you with that question over here. Can you move any thread flexibly to any lane? And the answer should be no. Even if you had an empty spot in a warp, and another, okay, let me see if I have an example over here. I should have an example, right? Yeah, there you go. Actually, that is good. Yeah, this one. So here there's an empty lane over here. This thread is in this lane. Can we move it over here? No, right? Because it requires data from the register file that's here. Because remember, we partitioned the register file into lanes. You cannot move it over here because when you move it over here, it will go to a register file and it will get the wrong value. Because only registers that are belonging to threads that were assigned to this lane are here. And you cannot get your data from there. Now, it turns out you could, but with a lot of additional complexity, which we're not going to go into that. Okay. Question? Okay. So I think I've given you these slides, so I'm going to skip that and cover one more concept, systolic arrays. Any questions before that? How many of you find this fascinating, by the way? Okay, good. I have a lot of hands. How many of you wouldn't even care about this? That's okay. You can. Okay, I see 2 hands, but they sound like jokes. Yeah, I find this fascinating because there's a lot of complexity in this, but there's a lot of beauty also, I think, in the processing model. So it's always good to think about, like, why have GPUs been so successful today and the programming model and the flexibility, everything we talked about has enabled them to be very successful. It's not clear if they will keep going to be that successful, because they're still at heart or internally a SIMD machine, right? They cannot do this difficult out-of-order execution at the moment. So if they really want to, if you want a GPU to really conquer the world and execute all kinds of programs, you will need to find a way of enabling it to extract this hard parallelism. It's still a machine that extracts relatively easy parallelism, right? It works really well if a lot of your data is parallel, and also you have thread parallelism. But it's not clear if it will work really well if those conditions are not fully true. Okay, so you've seen these slides before. You can go back and look at them. But let's look at systolic arrays very quickly. So systolic arrays are really interesting, I think. I'm not sure if I'll be able to go through all of these slides. I mean, actually, a better suggestion that I have is, do you have any questions on GPUs? Or do you want me to go through systolic arrays? I see. Okay, there's one question. Yes? Yeah? So this is the core, CUDA core. And that's why you have 30 of these. Okay? I've shown this picture a while ago, actually. Basically, you have 30 cores, 8 SIMD functional units per core. You can take a look at it. So who wants to go to systolic arrays very quickly? Or who wants to go home? Okay. I mean, I'm not sure if I'll be able to do justice to systolic arrays in the next 5 minutes. So I'd rather let you go home. Okay. Have a good weekend.